cases, sometimes they give scalar multiplication and the addition definition. So keep those two, and you have to check all the other properties. In such type of example, some examples I will give. Last time I gave right. Example is, let Rn be the set denoted by A1, sorry, A2, dot an where ai are from R and 1 comma I between. Have you got an idea about this set? So every element of the set is like this: A1, A2, A3 up to AN. For example, so in this, just one example: 0, 1, 2, 3, etc. Something like 0. This is the one element, no? N elements are here. N components are here. This is an element of Rn, right? N components are here. N components are here, right? So for given any u, for u comma v is in Rn are two elements where u is in the form A1, A2 up to An. How we can take v in the another element? So tell me. So this is a one element I have taken.
B1,
so,
B2.
Yes. We can take as B1, B2 up to Bn.
Yeah.
There are two different elements. Two different elements. So any two element of Rn is this. So let alpha be any scalar in R. So, right, define that addition and scalar multiplication. Define addition and scalar multiplication in the form of as follows. U plus V vector addition, then A1 comma A2 up to AN, B1 comma B2 up to Bn, right? So addition is follows like this: B1 component wise addition. Right? So scalar multiplication is defined like this: alpha time A1, A2, A. Alpha A1, alpha A2, alpha A. Okay. So the set is in the the set is Rn, those which contains infinite many elements, and so every element is of the form in Rn is defined that A1, A2 up to An. Now I have defined an addition and scalar multiplication in the form of this. This is a vector addition and this is a scalar multiplication. So now we can check that whether using this addition and multiplication, is it possible to be a vector space or not over the field R? Scalar field is R, no, over R. So we have to check whether this Rn is Rn vector space over R. Vector space over R. Is Rn vector space over R, right? So then how to check? Give me an idea now. So you have to go by one, no? Hello?
Hello.
You have to go check with using this addition and multiplication.
Are the 8 properties?
No. Yeah, other 8 properties, okay, no problem. So already 2 are given. So whether so this addition is in Rn. Is it clear that u plus v is in Rn? So this addition is given. This is the form of addition. First of all, you have to check that whether this addition is in Rn. Is it in Rn? මේක Rn එකේ තියෙනවද මේ set එක? මේ element එක? Yes, why it is the reason?
A and B are related to the R.
A1 plus B1 is also in the R. That means A1 plus B1 is as A1 and AB1. This is also a real number. Every component is also a real number. Therefore, the same pattern is there. Therefore, U plus V is in R. So, U plus V is in Rn as given definition. Right? So also, right, what is the next property in additive additive vector addition property? What is the first the next property? So addition is there. This is called closure property. Property holds. I forgot to give this word. Closure property holds. What is the next property I have to check? Commutative law. Right. Let U comma V is from Rn and check whether consider U plus V. Then A1, A2 up to AN plus B1, B2 up to BN. So which is equal to A1 plus B1, A2 plus B2, sorry, comma, AN plus BN. So how to check how to convert this one into commutativeness? Is it possible to write B1 plus A1? Because of this, A1 plus B1 is a real number, A1 and A also have a real number, so we can convert it. B2 plus A2, BN plus AN, right? So now I can write this one, B1, B2 up to BN plus A1, A2 up to AN, right? So this is V plus U. So now we can say that commutative holds, ne? Isn't it?
Yes, sir.
Commutative property holds. Commutative property holds. What is the next property?
Associative.
associativity. Let us take U, V, W from Rn. Then, so U, A1, A2, A3, B1, B2, B3, as well as W, we take C1, C2, C3 up to N. Okay. Now consider U plus V plus W. So A1, A2 up to AN plus B1, B2 up to BN, right? Plus C1, C2 up to CN. Right. Similarly, can you check with all the other properties?
Yes, sir, we can do.
Right. Now this is the pattern. If all the properties are satisfied, then we can say that this is a vector space. What is the additive identity of this? What will be the additive identity? I'm just asking. I'm not doing everything. So I'm just starting asking what will be the additive identity of this this Rn. Are there additive identity exist or not exist? If exist, what is the identity?
U plus V equal to 0, then
No, additive identity means if you take any element from Rn, if you add with that identity element, you have to get the same element U. Say U is any element of Rn, and so if you take if you take an addition with the identity element, you will get again U. So that is called. So then that will be the identity. So U plus
0.
identity. Zero means yeah, zero
Yeah.
element. That is the how it will be the pattern, right? So identity pattern will be zero element is in the form 0, 0 up to 0, isn't it?
Yes,
No,
sir.
don't put 0, 1, 0, 2. Just of all 0. Understand? Right. What will be the just a minute. What will be the inverse, additive inverse of this? So let us take U is the element, any element of V. U is any element of Rn, which is A1, A2 up to AN. What so if identity inverse element, additive inverse exists for that vector, what will be that additive inverse?
Minus value of the vector.
Minus value of the vector. How it will be that so say
Minus A1 minus A2 minus A3 to minus AN.
right, minus A1 minus A2 up to minus AN. That will be the inverse. So like this, A1 A2 up to AN plus minus A1 minus A2 minus AN. Then if you add with this one, A1 plus minus A1, like that it goes up to AN plus minus AN, right? 0, 0, 0. So this is the identity. After adding the inverse, you have to get identity. So this is the way, right? So in here, what will be the scalar identity here? Scalar identity is what? Scale identity.
1.
Exactly. Exactly. That is the point. 1 is the scale identity. So I think you have an idea. I think you can do this vector space. So you can check whether this is the vector space or not, right? Okay. So another example, let CB is equal to x plus IY, where x comma y is in R. What is this? What is this? The set of complex numbers. Set of complex numbers. And let Z1 comma Z2 is in C, and addition is defined like, and addition defined as Z1 plus Z2 is equal to, say, x1 plus IY1 x2 plus IY2. So x1 plus x2, x1 plus x2, IY1 plus. So addition is defined like this. Now in here there are two cases. Whether these set of complex numbers are two way we can think that. Whether when the scalar is R, whether this is complex space is vector space, whether scalar is complex numbers, whether this is vector space or not, right? So in here, first case, if you take a case 1, if the scalar is R, then check that C is vector space over R. C is a vector space over R. එතකොට මේකේ vectors ටික ගන්න කොතනින්ද මට කියන්න? Where we have to get from the vectors? Hello? Vectors ටික කොහෙන්ද ගන්න ඕනේ? කියන්න. Vectors ටික කොහෙන්ද ගන්නෙ මං? මෙහි vectors කියන්නේ මොකද්ද? complex numbers වලට. මෙතන vectors කියලා කියන්නේ complex numbers වලට. එතකොට vectors ගන්නෙ මොකද්ද? කොහෙන්ද? Yeah, we can. Yeah, we are taking from the complex numbers as a vectors here. Okay. Vectors. Understand? And scalars from where? From R. Then that is not a complex number. But addition, scalar addition is defined, and the vector addition is defined. So scalar multiplication is for alpha is in R, alpha dot Z1 is Z1 say Z alpha dot Z is equal to alpha dot X plus IY. This is alpha X I alpha Y. Alpha X I alpha Y. Is that clear? So in here, scalar definition is defined. Now, is it possible to check whether this is a complex, this complex set of complex numbers are vector field or not in over the space R? Space R ke check කරන්න පුළුවන්ද ඔයගලන්ට? So you have to do at home.
Yes, sir.
Right. So if this is a vector space, right, we call this is a real vector space, right? Real vector space. Called this is real vector space. If the case 2, if the scalar is from C. Now scalar is a complex number. Let alpha is from C. Then alpha can be written as alpha 1 plus I alpha 2. So what is that? In here, scalar is a complex number. In here, scalar is a complex number. Now, only thing is different from the above is, what is the difference? Is there any difference comes in additive properties?
No, sir.
No, additive property is same as. Only thing is we are only differentiate with in here is from the scalar multiplication and distributive law. Right. So scalar multiplication is defined like this: alpha time Z. So alpha 1 plus I alpha 2. Right. This is a scalar, just a scalar x plus IY. So where Z is from C, that is also complex. So, right. So just if you multiply this one, you will get alpha x minus beta y plus I time alpha y plus beta x. So this is the definition of scalar multiplication. Is this a complex number? Is this a complex number?
Yes, sir.
Yeah. Therefore, alpha dot Z is in C as well. Ne? Therefore, closure property hold for scalar multiplication. Understand? Alpha dot Z is in C. Therefore, closure property holds for scalar multiplication. So no change in above and here with the additive properties. Understand? Similarly, so go for other properties. Right. There are plenty of many more examples. Right. So there is another space is called capital PX, capital P, which is denoted by PX, where Px is equal to A naught A1x A2x. This is Pn. This is Pn. A2x squared ANXN comma A1 comma A2 up to AN is in R. So in here, Pn means polynomials of degree n. Polynomial කියන්නේ මේකට තමයි කියන්නේ polynomial කියලා. Polynomials of degree n. Okay, polynomials of degree n. So addition and multiplication is defined like this. Let px comma qx is from pn, then px plus qx is defined like a naught a1x up to anxn plus b naught b1x bnxn, right? So two polynomial. This is qx. This is actually px. Okay. So addition is a naught plus b naught, a1 plus b1 x an bn x power n. Okay, right. So this is the addition defined. So again, corresponding sangunika coefficients only you have to add a naught b naught b1. So whether this is a vector space or not, whether p, you have to check all the properties. So this is another example. You all do it at home. Okay, this is another type of, right. What do you mean by px is equal to 1? Which degree polynomial is this? Which degree polynomial is this?
0.
0 degree polynomial. What is this?
Three.
Third degree polynomial, right? Px is minus x squared plus x3. This is also third degree polynomial. This is also degree 3 polynomial. Okay. We have to check the highest degree in that polynomial. We can say that that is the polynomial of particular degree, right? So you can prove that that is also vector space.
Excuse me, sir.
Yes.
It's mean that there are many x terms and the largest index, we can say that the degree polynomial, is it correct or wrong?
No, I didn't get your question exactly. Yes, tell me.
There are many x terms in that example. The x
Yeah.
squared and x cube, like that.
So you are telling that, yeah, good. You are telling that in here 1 x squared plus x cube minus x x plus x cube, x squared plus x cube, like that.
Yes, sir.
No. So in here you have to see this. What is the highest degree?
Then cube, then it is not, we
This
can.
is actually, this is P3, no? No, not all the P3. P3 means all possibilities. All possibilities. These are few numbers. There are infinitely many, no? Because A naught, A1, A3. P3x means A naught, A1x, A2 x squared plus A3 x cube, where A naught, A1, A2, A3 are from R. Clear?
Yes,
So
sir.
all the possibilities, there are few. This is the subset of this P3. Say just say this is S, S is a subset of P3. So in here you have to see the highest degree. Which is the highest degree? Highest degree we got is X3, na?
Yes, sir.
So this is the set of some set of degree 3 polynomial, not all the collection, but few collections. So therefore, if you take the common general P3x, which is the subset of S is a subset of P3. Clear? Yes?
Yes, sir.
Right. So you have to check at home whether in this general case, whether this is, what is the 0 degree polynomial? What is the, what will be the 0 degree polynomial, additive identity of this polynomial space, Pn?
Index of the X is 0.
Index means, what do you mean? Not index. That is, you are telling these are index. A1, A node, A1, A2 up to An.
No, sir. Then x to the power 1, x to the power 2, then x to the power n.
Power of x.
Yes.
That is not index. Power of the, right. So the 0 degree polynomial is 0 degree polynomial Px is 0, 0 power x, 0 x squared, 0 x cube, like that, 0 x n. So this is called 0 power degree polynomial. Okay, you can, in that the other word you can write just 0, but you know that if it is a 7 degree polynomial, 7 zeros are there, 7 or 8 zeros. Understand? So that is called a 0 degree polynomial. Okay. Is there. Right. Another different type of x. Let Q be scalar. Q be scalar. And V is equal to A plus square root B, where A comma B is in rational number. This is our A and B are rational number. A and B are rational number. B is of the form A plus root B. So in here is scale. So is V vector space over Q. මෙතන different Q කියන්නේ rational numbers නේ. Rational numbers කියලා කියන්නේ මොකද්ද? What is the definition of a rational number? Definition of a rational number. What is the definition of a rational number? Definition of rational number, please tell me. Such that P comma Q is from Z integer and Q must be not equal to 0.
All positive, negative, decimals and fraction numbers including 0.
Right. Now tell me, yes.
The begida muru engala.
Vihidamuru engal.
Okay.
Right. What happened if Q is equal to 0? which is not in the set, right? Irrational set means, right, it is of the form P over Q. Is that 0 is a rational number? Is 0 rational number?
No.
Right. How we can say? We can write it 0 over 1. Then this is the form. Is it in the form, in this form? Yes. 0 over 1. That is in the form of P over Q. Right? So it is in Q. Right. Okay. Tell me irrational number. Then I have told how to tell in Sinhala for rational number.
පරිමේය
පරිමේය සංඛ්‍යා. පරිමේය සංඛ්‍යා. එතකොට irrational numbers වලට මොනවද කියන්නේ? පරිමේය සංඛ්‍යා නොවන ඒවට.
අපරිමේය.
Right. That's good. අපරිමේය. Right. So give me an example of අපරිමේය. විහිද මුරා එන්ගල්.
square root 3.
Exactly. Square root 3. One more.
Square root 5, 7.
Okay, that's okay. Different type of number.
1 divided by square root 5.
Okay. 1 over square root 5. All type of this element. What is this? Pi. E. Pi squared, pi cube, everything. Okay. These are called irrational numbers. You may ask a question. Why pi? Pi is 22 over 7, isn't it? Pi is equal to 22 over 7, eh? Hello?
Yes.
Sir.
Pi is equal to 22 over 7 means why it is a rational number? Why you are not asking that question? නැත්නම් හේතුව කියන්න pi කියන එක irrational number එකක් වෙන්න හේතුව. 22 බෙදීම 7යි කියන්නේ පැහැදිලිවම rational number එකක්. P is the form of P over Q නේ.
ඊට දශම වගේන් ගන්නිද්දී අර එක දිගට තියෙන දශම වෙනවනේ.
දශමයෙන් ගන්නේ ඇත්තටම මේක equal sign දාන්න බෑ අපිට. This is not equal to 22 over 7, but pi is approximately equal to 22 over 7. Nobody can written as pi equal to 22 over 7. It will be, right? It is approximately equal to 22 by 7. Okay, that's why we said pi is not equal to 22 over 7, but pi is not a complete number, right? So it is a fractional number as well as irrational number, right? Irrational number, right? Okay. So we'll come to the story here. So is it possible to prove check whether this is vector space or not? ඔයගොල්ලන්ට check කරන්න පුළුවන් නේ මේක ගෙදර. මම මේ example කිය යන්නේ. එතකොට how so let us take v1 comma v2 is from v. Then v1 can be defined as a1 plus root 2 b1. v2 is equal to a2 plus root 2 b2. Okay. මේක පැහැදිලිද?
Yes, sir.
කියලා elements දෙකක් ගත්තා. I have taken two elements from this set, v1 and v2, small v1 and v2. So it is of the form a plus root b, no? Every element is of the form a plus root b. A and b are rationals. In here, what are a1, b1? A1, b are from a1, b1 are from q. A2, b2 are from also from
Q.
q. So what will be v1, v2? A1 plus root b1 plus a2 plus root b2, right? So which is equal to a1 plus a2 comma square root b1 plus b2. Is this in the set v?
Yes, sir.
Yeah, v1 plus v2 is in v. So this is a closure property holds, right? So where we take from alpha? Scalar is from also from scalar alpha is from
Q.
q. Then what will be alpha time v1? Just
Excuse
v1.
me.
Yes.
So in the previous, the addition part, A1 plus A2 is the comma or plus mark?
This is here.
Yeah, yeah.
That is plus comma. Oh, wait. In here, I am sorry. This is wrong. Wait, I will do that. So I have added these two. Right. A1 plus A2 plus square root. Sorry, thank you. B2. Now, okay.
Yes, sir, it's fine.
Right. A1 plus square root B1. Right. Now I can multiply. Alpha is alpha A1 square root alpha 2 alpha B1. Now alpha A1 is that alpha A1 rational? Alpha A1 and alpha B1? These two are rational?
Yes.
Yes, sir.
Yeah. Then this is in V. Is it clear? So this is in V. Right? Okay. Right. I think you can do that. So you have to, when you come to the faculty, you have to show completely, you have to fill out what I have given as an example, and you have to show that those are vector space, and you have to submit as a first assignment. What are the example up to now I have discussed, and one or two example I will give. You have to fill it in the, take the CR book and put assignment 1 and take down all these one, and step by step you have to write it and submit. Right? Right. Let Q be scalar. Check whether the followings are vector space. Right? Right. So one more example. So this is at home you have to do. This is normal addition. Is A B root 2 C root 3 D root 6 where A B C D are from Q. So scalar for this V is Q. The second one A plus B minus 3. Right? Square root minus 3, yeah? And third one, so this is another example. Let R be the scalar here. Scalar is R plus vector space over R. R plus is defined like this. X is in R for X positive number. Right? So you write down in the CR book and submit as an assignment 1. Okay? As an assignment 1. Right? You have to check all the property whether whether if at least one of these property is not hold, so this is not vector space. Okay, right. Now we will come to subspace. Right. Okay.
So excuse me.
Yes, tell me.
Is that R or R plus?
This is R plus. Okay. Thank you.
Okay, sir.
Subspaces. Subspaces. Vector space, we also vector space. Subspace means not that much different from that. V. So already we know that what are the properties to satisfy for vector space. Subspace means if V is a vector space, V is a vector space over F. V is a vector space over the field F, over the scalar F. Let V is a vector space over the scalar F, and S is a subset. S is a non-empty subset. So S is a non-empty subset of V. You can understand what is non-empty means. At least one element must be there, ne?
Yes, sir.
Right, at least one element must be there. So S is non-empty and S must be a subset of V. If those things happen, and S should be a subset of V, non-empty subset of V, and S satisfied all the vector space property of V. What are the vector space properties satisfied by V must be satisfied by S over the same field. Over the same field. I will give the definition perfectly. Make a තේරුණාද? මට කවුරු හරි එක්කෙනෙක් කියන්න හරියට. In English or Sinhala or Tamil. Subspace of the vector space. Yes. Tell me what do you mean by subspace? Tell, right.
ශුන්‍ය නොවන උපකුලකයක් වෙක්ටර් ස්පේස්.
ශූන්‍ය නොවන උපකුලකයක් වෙන්න ඕන. ඒක විතරක්ද වෙන්න ඕනේ. වෙක්ටර් ස්පේස් එකක් දුන්නොත් ඒකට සබ්ස්පේස් එකක් කියලා කියන්නේ ශූන්‍ය නොවන උපකුලකයක්. ඒක ඒකත් වෙක්ටර් ස්පේස් එකක් වෙන්න ඕන අර කලින් වෙක්ටර් ස්පේස් එකේම ප්‍රොපර්ටිස් එක සැටිස් කරපු වෙක්ටර් ස්පේස් එකක් වෙන්න ඕන අර කිව්වපු same field එකේ. These are the condition, right? First condition is S must be non-empty. Second condition is S must be a subset of V. Right? Third condition is, right, S is a vector space over F. V is a vector space. V is a vector space over F. Then what are the three conditions? S must be non-empty. S must be a subset of V. S is a vector space over F. S කියන එක vector space වෙන්නත් ඕන අර same field එකේ මෙයාගේ V කියන එකේනාගේ field එකේමයි same definitions and subset එකක් වෙන්න ඕන and non-empty වෙන්න ඕන. Right? එතකොට අපි කියනවා subspace කියලා. Then we say that S is a subspace of V denoted by S like this. V. Okay, right. I will give the definition. Let V be a vector space over F. Let V be a vector space over F. Let V be a vector space over F. Then a non-empty subset S of V, then non-empty subset S of V is called a subspace of V subspace of V is called a subspace of V if S is also a vector space addition and scalar multiplication inherited from V. Same. Addition space addition and scalar multiplication inherited from V. Okay. ඒ කියන්නේ දැන් මට පැහැදිලි කරන්න කොහොමද කියලා කියන්නේ. ආයි පාරක් කියන්න මේක very important කොටසක්.
வீனிசல் வெக்டர் ஸ்பேஸ் ஒன்றிக்க போகல அதுல வந்து இப்போதோட 0 இல்ல சூன்யத்தோட இல்லாத
ரைட் வெக்டர் ஸ்பேஸ் V and field வந்து F and field இல்ல
ஓகே F ன்ற field இருக்க போகல சூன்யத்தோட இல்லாத ஒரு உபதோட S வந்து உங்களுக்கு V சப்செட்னு சொல்லலும் அந்த உபதோடன்னு சொல்லலும் என்ன கண்டிஷன் V வந்து வெக்டர் ஸ்பேஸா இருக்கணும்
V அந்த S உம் வெக்டர் V வெக்டர் ஸ்பேஸ் ஆயிக்குது S உம் வெக்டர் ஸ்பேஸ் ஆயிக்கணும் அதே vector addition and same scalar multiplication. Okay. Hello, sir. Right. Okay. That's fine. Right. Okay. Wait, I'm going to give an example. See an example. Let S is a subset of R2. R2 is a vector space. R2 is a vector space over R. R2 means like this. A comma B such that A comma B is in R. Okay. So S is defined like this. A comma 0 where A is in R. All the elements is of the form A comma 0. So whether this is a subspace or not. Right. Is that non-empty? First tell me solution. Solution. Is S is non-empty?
Yes.
Yeah, at least one element is there, no? For A is in R means, so S is definitely non-empty set. There are many elements, but S is non-empty. Is S is a subset of R2? Subset of R2?
It's given, right?
No, it's not given. Oh, right, already given, no problem. Even though if you are not given, also no problem. It says S is a subset of R2. S කියන එක subset of R2 ද?
Yes, sir.
Definitely, because A comma 0 is an element of R2 as well. Again, instead of B in here 0. Therefore, R2. So what are the scalar addition and multiplication here? A1 comma B1 plus A2 comma B2, which is equal to A1 plus A2, B1 plus B2. Okay. Alpha is from R, scalar multiplication A comma B. Right. Now you have to check that whether, so actually this is a vector space, is it correct? Make R2 කියන එක vector space යන්නේ. ඒක පැහැදිලිනේ මම example කරෙත් ඒකින්. දැන් මට චෙක මේ හොයන්න ඕන S කියන එක subspace යන්න. දැන් subspace වෙන්න the conditions දෙකක් satisfy කරලා ඉවරයි මේක. non empty කියන එකයි subset කියන එකයි හරි. දැන් බලන්න ඕන, now I have to check whether S is a vector space in the same addition and multiplication as R2. Is that clear what I am saying? Huh? මම කියන එක තේරෙනවද?
Answer, please.
So R2 is a vector space, no? That is no problem. R2 vector space I have proved in the very first last class. R2 I have taken as a V and show that this is a vector space over the field R. That is clear, right? මට පෙන්වන්න ඕනේ, මට හොයන්න ඕනේ. පෙන්වනවා කියන්නේ එක්කෝ S කියන එකේ format එක දීලා තියෙනවා. S කියන්නේ S වල තියන්නේ පළවෙනි component එක ඕනෑම real number එකක් වෙන්න පුළුවන්. හැබැයි දෙවෙනි component එක always 0 වෙන්න. right? මේකේ සාමාන්‍ය 1 0 තියෙනවා. minus 1 0 තියෙනවා. 1 half 0 තියෙනවා. ඒ වගේ මේ පළවෙනි component එක ඕන විදියට වෙනස් වෙන්න පුළුවන්, but දෙවෙනි component එක always 0. වෙන විදියේ element set එකක් තමයි මේක. Is it okay? So first component of this element is any real number. The second component always 0. Such a type of collection is S. Such a type of collection is S. S contain that. But we know that S is definitely non-empty and S is also subset of R2. Is that clearly S is a subset of R2?
Yes, sir.
Right. Now, I have to check whether, now you know that in generally, what is the addition and scalar multiplication of R2. Now, if S is a subspace of R2, S must be a vector space over the same field with same this addition and this multiplication. තේරුණාද මම කියන එක? එතකොට මේකේ අපි ගමු a1, 0, a2, 0 කියලා elements දෙකක් from S. addition එක කොහොමද එන්නේ එතකොට? a1, 0 plus a2, 0 is equal to ඒ කොහොමද addition එක එන්නේ?
A1 plus A2.
a1 plus
A2 plus.
a2 plus here 0 ne? Just 0 ne?
Okay, sir.
right. එතකොට මේකේ addition එක S වල තියනවද? දැන් මම සාමාන්‍ය addition එකක් විදියටනේ add කරේ මේක.
Yes.
දැන් මේ addition එකමනේ පාවිච්චි කරලා තියෙන්නේ. පළවෙනි compounds දෙක එකතු කරා, දෙවෙනි compounds එකතු කරා. ඒක හරිනේ. එතකොට now let alpha is from R and alpha into a, 0 and a, 0 is in from S. So then this is alpha 0, sorry, alpha A. Alpha 0 is 0 ne? Alpha times 0 is 0 ne? Hayyo.
Yes, sir.
Yes, sir.
Right. Mama me 300 දෙනකොට කෑ ගහනවා වගේ මේ is this the element of S?
Yes, sir.
Scalar multiplication එකත් හරි. Now you have to check all the other properties ne? All the other properties under this addition and this scalar multiplication. If those all 10 properties satisfied, S is a vector space over the same field as the R2 and same addition and multiplication. If so and so happened, we say that S is a subspace. Okay. So check the first property, commutative law. Is that commutative law satisfied?
Yes, sir.
Commutative law satisfied. Commutative satisfied. Right. Associative law.
Yes, sir.
Right. Associative satisfied. Right. Next one. Identity. Inverse.
Yes, it's okay.
Huh? Inverse. Let let a comma 0 is in S. Any element a comma 0 is in S. Then definitely, so first identity. So what will be the identity? Is that 0, 0 is in S. 0, 0, comma 0, comma 0 is in S.
Yes, sir.
Huh?
A is a real number.
Yes, neither.
Yes, sir.
Yes. It's perfect. Right. 0, 0 is in S. That is clear. Therefore, identity exists in S. If the fourth one is additive inverse. Additive inverse is if A is a 0, comma A comma 0 is any element of S minus A comma 0 also in S. Is it correct? A comma 0 is in S as well as minus A comma. So if you add A comma 0 plus minus A comma 0, then we say that A plus minus A comma 0, which is equal to 0 comma 0, which is identity. Which is identity. Okay.
Okay, sir.
Right. Right. ඒ වගේ අනිත් properties ටිකක් check කරන්න පුළුවන්ද? So check කරන්න whether this is subspace or not. Right. We will move to the important theorem. Very important theorem. This is very important. I will ask to prove in the exam as well sometime. Let V be a vector space over F. Let V be a vector space over F. Over F. And W is a non-empty, sorry. W is non-empty subset of V. Subset of V. Non-empty subset. දීලා තියෙනවා. Then W is subspace of V if and only if and only if the linear combination alpha, I will come to that later. Whenever alpha beta is from the scalar from W and sorry F and U comma B is from W. Now I will explain this one. V is a vector space over the field F. Okay. So in here given that so W is a subspace of V over the same field if and only if alpha U plus beta V, alpha U plus beta V is in W, where U comma V are from W and alpha beta is from. So if W is a subspace, alpha U plus beta V combination is in W. Already U and V are elements of W. Already given that non-empty subset කියලා දීලා තියෙන්නේ. ඒ condition එක ආපහු බලන්න නැහැ. දැන් බලන්න තියෙන්නේ මේ combination එක. මේ linear combination alpha U plus beta V කියන එක W වල තිබ්බනම් U, V, W කියන ඕනෑම එලිමන්ට් එකක් අපි ගත්තොත් U, V කියලා ඕනෑම එලිමන්ට්ස් දෙකක් W වලින් ගත්තොත් and alpha beta කියලා ස්කේලර්ස් වලින් ගත්තොත් ඒකේ combination එක alpha U plus beta V කියන එක W වල තිබ්බොත් if and only if W කියන එක subspace එකක්ද. හරිද? මේක තමයි prove කරන්න තියෙන්නේ. Make a very important proof. So the forward way I will start. Let W be subspace of V. W කියන එක subspace. මට පෙන්වන්න ඕනේ මොකක්ද එතකොට? ඉස්සෙල්ලා forward way එක. දැන් මේ පැත්ත. suppose කියලා ගමු. let කියලා ගන්න නැතුව suppose. Suppose W be a subspace of V. W කියන එක subspace එකක් කියලා ගත්තොත් මට පෙන්වන්න ඕනේ මොනවද?
alpha U plus beta V
is in W. Right? I have to show that alpha U and B plus beta V is in W, whether U and V are from W. So the subspace I have taken. So since W is a subspace, by definition, W is non-empty. W is a subset of V. Right? W is a vector space over F. W is a vector space over F. Is it clear?
sir.
By definition. Definition of subspace. Right. Now let alpha comma beta is from F and U comma V is from W. Right? Since W is a vector space over F, alpha time alpha U is in W. Is it correct? Scalar multiply with the vector. I have used the definition that W is a vector space. Subspace කියන්නේ already එකත් vector space එකක් වෙලා තමයි subspace වෙලා තියෙන්නේ. Only different is it is a subset. Alpha U is in W. Is it correct? Right, because already එක vector space එකක් වෙලා තියෙන්නේ. Similarly, beta V also in W. Is it correct? Yes.
Yes, sir.
Right. එතකොට මේක already W කියන එක is a vector space. Therefore, මේකත් element එකක් alpha U plus this implies that beta V is in W as W is a vector space over F. over F. Alpha U plus beta V, alpha U plus beta V is in W. Therefore, forward way is okay. Right, now reverse way. Suppose alpha U plus beta V is in W for alpha comma beta is in F and U comma V is in W. Already in the hypothesis it is given that it is given that W is a non-empty set and W is a subset of V. No need to prove these two. No need to prove these two. Understand? It is a general hypothesis for this theorem. I have to prove that. What I have to show now? Only one is remaining. Only thing is remaining to show. What I have to show?
Vector space.
W is a vector space over F කියලා කිව්වනම් I am done. If I can tell that W is a vector space, then I am done. Right. I will go for one by one property. Yeah. So this is given. So first property is closure property. No. If U and V are from W, already U and V are from W. Right. Let alpha is equal to beta is equal to 1. Take 1. Then 1 implies U plus V is in W for any U comma V is in W. Is it correct? Is that correct? So closure property holds. Any two elements U and V got U plus V is in W. I have substituted that alpha and beta can take any value. Scalars, no? Any scalars. Alpha and beta I have taken as a unit. Alpha and beta I have taken as a unit. 1. Okay?
Okay, sir.
Right. ඊළඟට මට බලන්න ඕනේ මේකේ 0 vector එක තියනවද කියලා. All right. So if U plus W is in U plus V is in W means the second property is automatically holds, no? U plus V is V plus U, no? Understand? Because this is holds means the second one, U plus V is in W means, right? U plus V is in W means U plus V is in W means U plus V is equal to V plus U. Why? एक reason එක කියන්න. U plus V is in W implies that U plus V is equal to V plus U commutative holds. Why? එකක් මතක තියාගන්න W කියන එක always subset of V. ඒ කියන්නේ U plus V කියන්නේ W වල තියෙනවා වගේම U plus V කියන්නේ V වලත් තියෙනවා. U plus V is in W as well as V because W is a subset of VWV. Right? Right. Because W is a subset of V. Because W is a subset of V. U plus V is in W, therefore U plus V satisfied the vector addition, vector commutative property in as a elements of V, therefore U plus V is V plus U by V, but U plus V is in W, therefore V plus U also same in here. මේක තේරුණාද නැද්ද?
W උපතොරෙන්
Right. Reason I will shall I tell you in Tamil? Right. Hello.
Yes sir. Okay.
U plus V. W is already a subset of V. V is a vector space. Ne?
Yes,
V is a vector space. Right? V is a vector space. Upper U plus V already V le virkidane.
Oh.
U plus V is in W as well. U plus V is in V. Is it clear?
Yes sir.
V is a vector space over F. Is it clear?
Yeah.
Therefore, U plus V is equal to V plus U because U plus V is in V. Is it okay?
Yes sir.
Right. U plus V is in V. Is it okay? Right. But U plus V is equal to V plus U because V is a vector space. But U plus V is in W, but these two are equal. Therefore, V plus U also in W and U plus V is equal U plus V is equal to V plus U. Okay? Have you got the reason? Right.
Yeah.
So similarly, associative property, the same reason. You always think that these all elements are the elements of V as well. W is a subset of V. W වල තියෙන same element ටික V වලත් තියෙනවා. V කියන එක V is already a vector space. Okay.
Okay sir.
Right. එතකොට identity element එක කොහොමද හොයන්නේ? alpha U plus V. එක පාවිච්චි කරලා. So now the second property is associativeness. Associative. First, second, third property. How to show identity element is 0, no? Additive identity is 0. So if alpha is equal to beta is equal to 0, what will happen to alpha U plus beta V? And alpha U plus beta V, what will happen? Alpha U
0.
Z equal to 0. Alpha and beta are any scalars, no problem. But alpha U plus beta V is always for any scalars. Alpha U and beta V is W. Therefore, this is in W. Therefore, 0 element is in W. 0 vector is in W. Right? 0 vector is in W. Right. Right. Now I have to show that now additive inverse. In yesterday I proved, day before yesterday I proved that for for all u, for this is proved that for all u is in V is a vector space OF, minus u is equal to minus 1u. Make a mahitana third part with your proof kara yesterday theorem ekak. Ehema neda? I'm going to use this theorem now. Harida? Make a proof kara neda mom. Go back to your notes. Theorem, there are 3 conditions proved. The third condition, I think this one.
Yes, sir.
Yes, vector space, right. Now, since alpha u plus beta v is in W, right? Let alpha is equal to -1 and beta is equal to 0. Any scalars I can think that. Therefore, minus 1 time u plus 0 no, is in W. Sorry, is in W. Okay. Minus 1 time u is in W. But minus 1 time u is equal to u by theorem. By theorem. Therefore, minus u is in W. So for all u is in W, their x is minus u is in W. Therefore, invertible, additive inverse. Therefore, additive inverse exists. So all additive properties are satisfied. All additive properties are hello. 5 properties satisfied. So how many properties to satisfied next? So scalar multiplication. Scalar multiplication is there, no? So what is the 6th property? Right. Alpha u plus beta v is in W. Right? Beta let beta is equal to 0. Then alpha u is in W. So closure scalar property. Alpha u for roll u is in W. That is okay? මම බීටා කියන එක 0 කියලා ගන්නවා alpha any element එකක්. එතකොට alpha u කියන එක කොහොමද තියෙනවා. right? මම මේකෙන් තමයි මේක ඔක්කොම prove කරගෙන යන්නේ. alpha u plus beta v. What is the 7th property? Scalar multiplication වල. Alpha u is in W for all u is in W. So the next is the 7th is let consider alpha plus beta u is in W. Why? What is the reason? Alpha plus beta u is in W. Why? What is the reason? And reason. Oh, so this is any scalar. I am telling that alpha u plus beta u is equal to alpha plus beta u. This is let u is equal to v. Now I am equating two vectors. If u is equal to v, we have alpha u plus beta v is in w. So instead of v, I put u. Alpha u plus beta u is equal to alpha plus beta u. Because of this is in w, therefore this is in w. Okay. So alpha plus beta u is equal to alpha u plus beta u. So what is the next? Right.
So excuse me.
Tell.
This is coming under the distribution law, right?
Yes. This is coming under and distribution law. I missed the orders. So what is the order?
For that we need two scalars and one vector.
Child. Okay. Okay. So already alpha u is in w. This is the vector. Alpha u, total alpha u is a vector. Okay. Total alpha u. Right. Let us take this as a u1 is alpha u. Then u1 is an element of w. Okay. Okay. Now let beta is another scalar. Then already prove that beta u1 is in w. Beta u1 is in w. Is it okay?
Yes,
Beta u1 is in w. So beta into this is alpha u in w. Right. Beta alpha u is in w implies that beta alpha also u is in w. Why? Already this is an element of v as well. Beta alpha u is in v. Since v is a vector space, beta alpha u is nothing but beta alpha u. Okay. Because the reason is this is the vector space element. So since this is in w, therefore beta alpha also in w. Therefore beta alpha u is equal to beta alpha u. That property holds. So those two. What is the next property? Distributive law.
Scale identity.
Scalar identity. Right. Scalar identity. Just wait. Right. Now already we know that alpha u is in w. Ne? So if alpha taken as 1 into u, which is equal to u, is in w. Therefore, this is scalar identity. That is simple, very simple. Okay. Right.
Yes. Okay.
Right. What is the next one? This is the 8th one, I think. Distributive law.
Distributive.
9, 10 properties are there. No? Right. Let u is equal to v. Since alpha u plus beta v is in w, alpha u plus beta v is equal to alpha u plus beta u. Because u and v are here same, therefore alpha plus beta is equal to u. Why this is the reason? Alpha u plus beta u is equal to alpha plus beta u, because u is an element of v as well. Right? Already u is a vector space element, therefore this is true. So this is true because of this. because of this reason, this. So distributive holds. Now the 10th property, let alpha is equal to beta. Alpha u plus beta v is equal to alpha u plus alpha v is in W. So this is equal to alpha u plus v, because u comma v element of v. Therefore, alpha time u plus v is equal to alpha u plus alpha v. So all the properties hold, or the vector space properties holds. Therefore, W is a vector space over F. Therefore, W is a subspace of V. Right? So this is a very important theorem. I'm going to summarize. I'm going to summarize again. Time is running out very fast. All right. Yes. So theorem says that let V be a vector space over F. W is a non-empty subset of V. Then W is a subspace of V if and only if alpha u plus beta V is a subspace of V if and only if alpha u plus beta V. Right. So I have first I have take the forward way. Suppose W is a subspace of V means, according to the definition, W is non-empty, W is a subset already given. W is a vector space over F. So alpha, if you take any alpha and beta and u and v, so alpha u is because of vector, W is a vector space over alpha u is there, beta v is there. Addition is there because of the closure property. Therefore, done. Forward way is done. The reverse way, I have used the alpha u plus beta v combination to show that already given that W is a non-empty and W is a subset already given. I have shown that W is a vector space over the same scalar multiplication and addition, vector addition in V over the field F. So that I have done one by one. So you have write properly all 10 properties and show that this is W is a vector space over F. Then we say that W is a subspace of V. Okay. Right. Any questions? Right. Example, let S is a set. Let S is a set A, B, C, D such that AB minus AD minus CB not equal to 0 and A, B, C, D are real numbers. Okay. So this is the set of all 2 by 2 matrix which are invertible. Invertible 2 by 2 matrix. Determinant is non-zero. Determinant of non-zero 2 by 2 matrix. This is vector space. I think I have given to prove this one. Neither. මේක මම දුන්නේ prove කරන්නනේ as homework and show that m is equal to a b c d where x m is equal to x y z r such that xr minus yz is 1. Show that M is a subspace of S where that. How to show? Using the above theorem, easily you can show that. So you have to take two elements from M and show that M is a subspace over R, over the field R, right? So solution. So I will take two elements, x1, y1, z1, r1, comma, x2, y2, z1, r2. So from this one, x1, r1 minus z1, y1 is 1. That means the determinant of this metric is 1, as well as x2, r2 minus z1, y2 is 1. Right, these are the known things. Let us take any elements alpha, beta is from R. Okay, and consider alpha time x1, y1, x1, y1, x2, z1, r1 plus beta time x2, y2, z2, r2. Right? Okay. You know this condition. Now I will multiply inside alpha x1, alpha y1, alpha z1, alpha r1, beta x2, beta y2, beta z2, beta r2. Right. Okay. Right. Add these two. If you add, what will happen? Alpha x1, beta x2, alpha y1, beta y2, alpha z1, beta z2, alpha r1, beta r2. Okay. Right. What I have to show the next. So if you if this total matrix would be in M, what should happen? මේක M එකේ තියෙන්න ඕන නම් මේ matrix එක දැන් මේ linear combination එක M එකේ තියෙනවා කියලානේ පෙන්වන්න ඕනේ. සමහර දැන් මම දන්නේ මම හිර වෙයිද දන්නේ හිර වෙන පාටක් තියෙන්නේ. එතකොට vector space subspace එකක් වෙන්නේ නැති වෙනවා. හරි. දැන් මේක දැන් මේක මේ m එකේ තියෙන්න ඕන නම් අන්තිමට හොයාගන්න මේ මෙට්‍රික් එකේ ඩිටර්මිනන්ට් එක මොකද්ද වෙන්න ඕනේ? What should happen? That should be 1. That, but what is the determinant of this matrix? Alpha x1, beta x2, alpha r1, beta r2 minus alpha z1, beta z2 into alpha y1, beta y2. Right. Simplify. Make a sulu කරන්න බලන්න. Right. Alpha squared x1 r1, alpha beta x1 r2, alpha beta x2 r1, beta squared x2 r2. හරි නේද? Minus alpha squared z1 y1 minus alpha beta z1 y2 minus alpha beta z2 y1 plus beta, sorry, ekat minus beta squared y2 z2. So I can take out alpha squared separately. Alpha squared, if you take out x1 r1 minus z1 y1. Right. Next, I can separate it. Beta squared x2 r2 minus y2 z2. Next, I can take it alpha beta x1 r2 minus, sorry, x1 r2 x2 r1 minus z1 y2 minus z2 y1. Okay, so this is 1, I think. Ne? In here I have got something 1. This is 1, but alpha squared time 1 plus beta squared time 1, but this is not equal to 1. So anyhow, this is not equal to 1. Is it clear? This is total determinant is never equals to 1. Sometime, but not always equal to 1. ඒක පැහැදිලිද?
Yes, sir.
Yeah, එතකොට මේක subspace එකක් වෙන්නේ නැහැ. මම show that කියලා දුන්නා. Right, okay. Therefore alpha x1 y1 z1 r1 plus beta x2 y2 z2 r2 is not in M. Definite, therefore M is not a subspace of S. එතකොට මේ theorem එකෙන් easily I can identify whether this is subspace or not. Clear? Right. Okay, that's all I have done up to subspace. So next we have to go to linear span, and I'll stop here. If you have any question, now ask. Is what I have given to do at home as an example, which is an assignment. Understand? So there are several examples I have given to show that those are vector spaces. Okay. So take one CR book, take one CR book and put first page you put assignment 1 and note down the problem what I have done here, and one by one you have to show every properties of the vector space and to show this is the vector space. That is the way of writing the assignment, and keep it with you. So you will be coming here next month. Okay, we are planning to get into inside. So not in confirm, maybe on the 11th we are going to get you. Have you got that message? So still the initial the initial talks are going regarding that. So when you come to the faculty, you have to bring with all the exercises. After coming here, sometime I will give directly the mid-semester exam. So what I have teach here, what I have taught in the online class, right? So you have to study at home and come. So we have a plan and take it. After coming back to here, you can't go home, because you will be quarantined for 14 days and you will be a pool or bubble.